Welcome back, students. In this video segment, we will look at the final section for our course, section 5.2, Polar Equations and Graphs. In the previous section, section 5.1, we looked at an introduction to graphing single points in the polar plane, and we laid the polar plane right on top of the rectangular plane, and we were able to see the relationships between the rectangular coordinates x and y and the polar coordinates r and theta of single points. In this section, we scratched the surface. We just scratched the surface of graphing entire equations in the polar plane. And to remind you, what we get by graphing equations is curves. And you've seen some curves in your intermediate algebra course. You saw parabolas, and sometimes you saw circles and lines, definitely lines. You had slopes and intercepts of lines and so forth. Even you studied logarithm curves, you studied exponential curves. We do a similar thing in this section. We would like to look at just the bare beginnings of graphing polar equations. So let's start with reviewing very briefly the first method you probably learned for plotting equations in rectangular form, and we're going to use that method to graph polar equations. Okay, so for example, let's sketch something simple. Let's, for example, get a thicker ink here. Let's sketch the graph of y equals x squared. Okay, a very common graph, or a very common equation to graph in intermediate algebra, sometimes in elementary algebra nowadays. Okay, so the first way you probably learned how to graph was to construct a small chart of ordered pairs, and then plot those ordered pairs and connect the dots. It's not the method we use in calculus and more generally in the sciences, but it gives you an idea of how graphs are formed. So let's do that. Let's just review real quickly how you would graph for the very first time something like y equals x squared. What you would do, or what your instructor probably suggested, is to construct a small chart of ordered pairs, and you were free to select x values, and you substitute those x values into the chart, into the equation, and get the y values. So very commonly we select simple x values like 0, 1, let's say 2, maybe -1, and maybe 1/2. Okay, and then you substitute those values into the equation. You get y equals 0 squared, or 0. If x equals 1, y equals 1 squared, or 1. If x equals 2, y equals 2 squared, or 4. If x equals -1, we get -1 quantity squared, which is 1. And for x equals 1/2, 1/2 squared is 1/4. Then, as I mentioned a second ago, you plot these points. And let's see how we want to do this. Let's say if this is x equals 1, here's y equals 1, y equals 2, 3, and 4. If x is 0, y is 0, so the origin is one of our points. If x equals 1, y equals 1. If x equals 2, y is 4. So this point corresponds to 2 and 4. If x equals -1, y equals +1. And just to round things out, if x equals, say, 1/2, then y equals 1/4. And then you took a big leap of faith. You took the leap of faith that you can connect these dots into a nice smooth curve, which is not necessarily the case in general. But for starting to learn how to graph points, it works out pretty nice. Okay, so we connect these dots, and we get a graph. Oops, I kind of missed that last one here. Let's see if oops, I missed it again. Wow, I'm not doing too well today. Okay, so this is the technique I want to use for graphing a polar equation. And then I'd like to give you a kind of a technique of using your graphing calculator to really quickly get the image of a polar graph. Okay, so that's pretty much the extent of the graphing that we're going to do in polar form. When you take a second semester calculus class, the instructor will probably, actually most definitely, review this with you and give you especially if you take me for Calc 2, I know this will be true, then the instructor will very likely give you a really much more efficient way of graphing polar equations or polar equations. Okay, in any case, let's get started. Okay, so let me thicken up my pen again. Let's start with one more rectangular equation, just to round things out. So suppose I said sketch y equals 2. Okay. Now again, you've graphed lines in elementary algebra, then you graphed lines again in intermediate algebra, so you probably recognize this as a horizontal line. But let's just take a look at the graph real quickly here. Now, there's no need to construct a chart of values, but the chart of values can still be constructed here. Notice that the x variable is missing from this equation, which is just fine. This is saying that no matter what x is, y must equal 2. So if I let x equal 0 or 1 or 2 or -1 or 1/2, the same x values I did before, what's y going to equal? 2. And this is pretty convincing that this is going to be a horizontal line. No matter what you let x equal, no matter where you go horizontally in the xy plane, you always go up 2 units. So if you always go up 2 units, you're graphing a horizontal line. So I'm going to graph the line first. Then I'll kind of backtrack to justify this. Let's see. Here's a nice horizontal line. Y equals 2. Let's see here, sticking up my pen. Okay, so if x equals 0, y equals 2. If x equals 1, y equals 2. If x equals 2, y equals 2. If x equals -1, y equals 2. And these are just a few points. If x equals 1/2, y equals 2. Well, if you keep doing this, you're going to get more and more and more and more dots that are going to be tracing out, which is pretty clear to be a horizontal line. Okay, I chose this second equation to review because the first equation I'd like to sketch in the polar plane is missing one variable as well. Suppose I want to sketch r equals 2. Of course, in the polar plane. In the polar plane. Or in the rectangular plane where the polar plane is placed right on top of it. Okay, now we don't construct a chart with x's and y's. We construct a chart with theta and r, and theta is missing from this equation. Okay, so, well, very commonly we choose for theta not values like 1, 2, and -1. We choose values that are much more familiar to us, like 0. These are angles. Pi over 6, pi over 4, pi over 3, pi over 2. These are the special angles in quadrant 1, and also 0 and pi over 2. And then what's r going to equal? Well, r doesn't depend on theta. No matter what we let r equal, no matter what we let theta equal, r's got to equal 2. Now, can you imagine what the graph is going to be before I actually graph it? Remember, theta sweeps out angles either positive counterclockwise or negative, which would be clockwise. And no matter what we choose for theta, r must move 2 units from the origin. Remember, the r value comes out of the origin. So if we always go 2 units away from the origin in the radial direction outward, what are we going to get? We're going to get a circle. Okay, if you're not sure about that, magically here's our polar plane, and I've graphed the polar plane. I'm going to use this drawing through the lecture. I've graphed the special angles. I've graphed theta equals pi over 6, pi over 4, pi over 3, theta equals 0, theta equals pi over 2, etc., etc. The usual for our course. Well, if theta equals 0, r equals 2. Theta equals 0, r equals 2. So let's put r equals 2 right about here. R equals 2. If theta equals pi over 6, r equals 2. So if there's pi over 6, and here's r equals 1, r equals 2. Theta equals pi over 4, r equals 2. No matter what we let theta equal, r is going to equal 2. What are we going to get? We are going to get, let's see if I can do this. We are going to get a circle. We're going to get a circle in the wrong place. Let me see if I can do this. I didn't practice this ahead of time. I was hoping this would just work. Ooh, let's see if I can do this. Bear with me. I should do this off camera, huh? I will do it off camera if it doesn't work out. Well, there's my circle. It's just not hitting the points. Let's stretch out the circle, make it fit. Here we are. That's sort of going to work out. Ooh, there's the center. You're very patient with me here. That's probably as fast as I'm going to do. Nope, I had it better. Oops. Next semester, I think I'll do this work off camera. Okay, that's good enough. Okay, maybe I should have put the circle in first. When theta equals 0, r equals when theta equals 0, r equals 2. When theta equals pi over 6, r equals 2. Pi over 3, r equals 2. Pi over 2, r equals 2. You get a circle of radius 2. So in the polar plane, r equals a constant gives you circles centered at the origin. Okay, well, this isn't very exciting. So let's really get to the reason for the season here, so to speak. Let's see what we get by sketching. Oops, I should put the directions in, huh? Let's see what we get by sketching something a little more elaborate. This is going to take us a little time. Okay, so let's do that. All right, first of all, we need to construct a chart of values. Now, the values that we construct for the ordered pairs for r and theta, the size of that chart really depends on us. We graph enough points to get an idea of what the curve maybe looks like. Okay, so what we're going to do is we're going to choose 0, or choose angles that are familiar to us. 0, pi over 6, pi over 4, pi over 3, and pi over 2, and we'll see what happens. So if theta equals 0, I get r equals the sine of 0, which is 0. Theta equals pi over 6, we get r equals the sine of pi over 6. These are all familiar values to us, which is 1/2. Sine of pi over 4 is radical 2 over 2. Basically, I'm going around the unit circle. The sine of pi over 3 is radical 3 over 2, and the sine of pi over 2 is 1. Old values for us. Now, we have to plot these points, these numbers as points. So I'm going to round each of these numbers to 1 decimal place. Well, 1/2 is exactly 0.5. Radical 2 over 2 is approximately 0.7. Radical 3 over 2 is approximately 0.9, and 1 is 1. And 0 is 0. Okay, so as theta goes through the first quadrant, the r values go from 0 to 1. The r values go from 0 to 1. Let's plot those. Let's plot these points. Okay, so we're going to need magically another set of axes, so give me 2 seconds. Okay, so here's our set of axes again with the angles. If theta equals 0, r equals 0, that gives us the oops, I have my pen on eraser. Gives us the origin. If theta equals pi over 6, we're at 0.5. So let's see. I'm going to call this value 0.5, and this is 1 along the polar axis. So this is 0.5, and this is 1. So if theta equals pi over 4, then I'm at pi over 6, I'm at 0.5. When theta equals pi over 4, I'm at 0.7, so 0.5, 0.6, 0.7, 0.8, 0.9. So I'm right about, let's see, let's actually do that right about here. And then at pi over 3, I'm at 0.9. And I could do a little better than that, I guess. So that's all right. And at pi over 2, I'm at 1. So at pi over 2, I'm at 1. Let's see if this is 1. I'm going to move it, swing it through there. So we're getting a series of points. Okay, and we keep going. We keep graphing these points until we're sure we have or we're fairly certain of what kind of a curve we're getting. So we're going to keep going. Okay, this is not the way you're going to do this on your exam. On your exam, you could use your calculator to get an image of the graph. But I want you to see how graphs are formed. So let's take a look at angles in quadrant 2. And angles in quadrant 2, to pick up where we left off, would be, what would the next angle be? It would be 2 pi over 3, then 3 pi over 4, then 5 pi over 6, and then pi. So at 2 pi over 3, well, in quadrant 2, the sign is still positive. The sign is still positive. Remember, all students take calculus. All students take calculus. In quadrant 2, the sign is still positive. So the sign of 2 pi over 3 is the same thing as the sign of 1 pi over 3, which is 0.9, approximately. Okay, so at 3 pi over 4, the sign is the same thing as it was at 1 pi over 4, because the sign is positive in quadrant 2. At 5 pi over 6, the sign is the same thing as it was at 1 pi over 6, which is 0.5. And the sign of pi is 0. And we draw these points. So at 2 pi over 3, we get the same r value we got at 1 pi over 3. Okay, so that at r value at 1 pi over 3 and the r value at 2 pi over 3. The same at 3 pi over 4, we get 0.7. Same as we got for 1 pi over 4. And at 5 pi over 6, we get 0.5. We get the same r value we got at 1 pi over 6. And the sign of pi is 0. So we can kind of see a curve kind of emerging out of this. Okay, I'm going to take my life in my hands here and attempt to draw this curve. We connect the dots. You can kind of see a closed curve. Now we can't assume that the shapes of these objects are circles. In fact, very most often actually the polar curves are not going to be circles. Okay, so, but we can kind of connect these points as if they are going to be circles. So we go. Let's see if I do this. Make my pen lighter. Okay, I'll do it. Let's do this. Here we go. Here we go. Looks like you're getting a closed curve. I'm afraid to look. Oof, it's terrible. Terrible, terrible, terrible. Okay, let me see if I sneak in the other way. That's a little better. Could have been much worse. 30 years of teaching and my graphs never get good. Okay. This graph does turn out to be a circle. It does turn out to be a circle. But like I said, it's very rare that your graphs in polar forms represent circles. They're usually other objects, other kinds of objects. Very often they are closed curves. They're curves that loop around, and it's very convenient to use polar form for those types of curves. So let's continue. But we're not really we haven't gone through one complete revolution. What about quadrants 3 and 4? So let's continue. Let's take a look at angles in quadrant 3. Okay. Well, in quadrant 3, we're looking at 7 pi over 6, 5 pi over 4, 4 pi over 3. I'm going around the unit circle in terms of the angles, and 3 pi over 2. Now in quadrant 3, the sign is negative. Okay, all students take calculus. Quadrant 3, the tangent and cotangent are positive, so the sign is negative. So at 7 pi r 6, our next angle, the sign is not going to be positive, it's going to be negative. It's going to be the opposite of it was at 1 pi over 6. So we have negative 0.5. And at 5 pi over 4, we get the opposite of what we got at 1 pi over 4, negative 0.7. And at 4 pi over 3, that last angle just before 3 pi over 2, get the opposite of what we got at 1 pi over 3. And at 3 pi over 2, we get negative 1. Okay, so if we're getting a graph in quadrant 3, how could this be a circle? Well, look at the r values, they're negative. When theta equals 7 pi over 6, I'm going to switch to my dots to colors to red. When theta equals 7 pi over 6, when theta equals 7, there's our theta, 7 pi over 6, r isn't positive 0.5, it's negative 0.5. If it were positive 0.5, it would shoot out this way. That would be positive 0.5. The r value is not positive 0.5, it's negative 0.5. So when theta equals 7 pi over 6, I get r equals negative 0.5. That dot is right on top of the dot I had in quadrant 1 at 1 pi over 6. At 5 pi over 4, the r value is negative 0.7. At 5 pi over 4, the r value is negative 0.7. I'm going to get I'm going to be overwriting. I'm going to be putting a dot right on top of the dot I had in quadrant 1 at 5 pi over 4. So I'm tracing this circle again. At 4 pi over 3, I have the r value is negative 0.9. I'm back in quadrant 1. At 3 pi over 2, the r value is negative 1. So I'm tracing out the circle again. Okay, if I were to look at quadrant 4, the r values would be negative again. The negative again. The sign in quadrant 4 is negative. So in quadrant 4, the angles would be in quadrant 4, but the r values would be back in quadrant 2. So what's happening in this case is that as theta goes through one complete revolution, we trace out this circle twice. In any case, we get a circle. We get a circle out of this, and it only takes theta going from 0 to pi to get the complete graph of the circle. And this is not something we can generalize to. It doesn't. This is not saying that it only takes theta equal pi to get the complete graph of a polar curve. Okay, we just happen to only need pi from 0 to pi for theta for this particular graph. Now, what I'd like to do is I'd like to give you an introduction to how to use the calculator to get these graphs. It's very simple. It's very, very simple. Okay, so let's take a look at our next example, which is going to be to graph the same graph, but using our calculator. Use a graphing calculator. Calculator to sketch r equals, I'll write it on I'm going to keep it on the same line. R equals sine of theta. Okay. So there are 3 steps to doing this. Step 1. Put your calculator in the correct mode to do this. We need to be in the radian mode. And we need to be in the polar graphing mode, POL. Okay, and I think I'm going to do this as I lecture, so I'll make sure that I do this correctly. Okay, so I'm turning my calculator on and making sure that it's in. I'm using a TI-84 calculator. And then push mode. Okay, so radians, polar. And once you do that, push second quit to get out of there. The second thing, we need to enter the function. Okay, so you push y equals upper right, and you notice that the calculator doesn't say y1, y2, y3, etc. Like when we were graphing trig equations before. It has r1, r2, so it's ready for you to enter r equals a function of theta. So you push y equals, and you enter r1 equals, and then push the sign button, sign, and for the variable you use the xt theta n button, xt theta n, and for the calculator, since it's in the polar mode, it knows that it's interpreting that button as the theta button and not the x button or t button or n button. Okay, so that's the second thing. We push sign of theta and close the parentheses. Okay. Now, if we push graph right away, our graph's going to suck. If we push graph right out, that the viewing window was probably very bad. So we need to change the viewing window so that we see a nice graph of this. If you pushed graph and you got a nice graph, you got lucky. Okay, so we have to change viewing window. Okay, so viewing window. Viewing. I'm spelling today. Viewing window. And to do that, we push window. Actually, no. Sorry, scratch that. To do that, we could do that. We want to tell the calculator to do two things. We want to tell the calculator to fit the graph of the complete graph of the curve exactly in the screen. So to do that, we push zoom, the middle button on the top row, and fit. And if you notice, it's not in that list there, but if you push the cursor downward, or the downward button, you notice that zoom fit is number 0. So you can get the cursor down to 0, or you could just type in 0 and then enter. So zoom 0. And then what the calculator does when you push zoom 0 to zoom fit is it gives you a smashed version of the graph. Why isn't it giving you the circle shape? Well, the shape of the screen is not square, so it's exactly fitting what you entered in, the curve you entered in, but it's smashed because the screen is actually rectangular, not square. So then you tell the calculator, and this is the last part of the third step, is to accommodate the fact that our calculator's physical viewing window is rectangular, and you push zoom square. So you push zoom again, and square is number 5. So I just push zoom 5. And that will give you a nice, better than my graph, of course. That'll give you a nice square-shaped, not square-shaped, nice circular-shaped graph. So zoom fit, zoom square, zoom fit, zoom square. Okay. So what I'd like to do to end our video segment is to graph one more using the calculator. So sketch with calculator, calculator, r equals 1 plus sine theta. Okay, so we're going to do this. First thing, well, we don't have to do step one. Step one was completed already. Step one, done. Okay, once you change the mode, it's done until you change it back. So if you want to graph in the rectangular coordinates, then you have to go change that polar back to rectangular. Leave it in radians, but change the polar back to rectangular. Okay, so let's see. Actually, we did change polar back to function. Function. The calculator's rectangular mode is called function, F-U-N-C. So 1 is done. 2, enter the function. So we push y equals, and you push clear to clear out the sign. Or you could just add 1 to it. I would just start over. Enter R1 equals 1 plus sine, and then push the xt theta n button. Okay, so these are all buttons. And then close the parentheses. So 1 plus sine xt theta n, and then close the parentheses. And then do the 2 zoom fit, zoom square things. Push, you don't have to push exit or anything, just push zoom. And it was number 0, so you can push the downward button until you get 0, or you can just enter, push 0. And what shape do you get? What does it look like? What does it look like? It looks like sort of a pumpkin, upside down apple, not quite a heart shape. It's actually called a cardioid. Cardioid. Let's see if I can graph it. This is a cardioid. Cardioid. Cardioid, the word cardioid, it means heart-shaped. Heart-shaped, shaped like a heart. But this is a smashed version of the cardioid. So you push zoom fit and you get the cardioid shape. If you push zoom square right after that, you get its more realistic shape. Its realistic shape would be pretty similar to the smash shape, I guess. You should see this appear, something like this in your calculator. Zoom fit, zoom square. Okay, and that's it. So when you do the homework, if you've got time from this section, sketch 1 or 2 of the homework problems by hand, constructing the chart if you've got some time. But definitely sketch them using the calculator. It's very simple. It's a very simple matter. You change the mode, the correct modes, radian mode and polar mode, enter the function, step 2, and then push zoom fit, zoom square, and you should see really, really quick and nice images. And that's it. That takes us to the end of our video segment. And I am looking forward to talking with all of you again very soon.